So I will start at this point. I won't give you to wait too long. So good day to everyone. First of all, I would like to welcome and thank everyone for participate and all the efforts that you made in registering to this webinar, to this first webinar. Actually, we have right now about more than 250 attendees. And actually, the number of people who registered to this webinar is more than 600. So as I said, it's quite impressive. Actually, we have here people from more than 68 countries, okay? 68 countries, different languages, different time zones. So it was quite challenging of decide on the precise hours that it will be as much convenient for most of the people. Actually, we have here an audience from more than 50 people from Brazil, a large audience from the United States, from Ireland, from South Africa, from the UK, Spain, Italy, India, Israel, and many other countries. So basically, I believe that most of you are right now under a lockdown. So first, I hope that you are crossing it as easy as possible. And for the people which are already in the steps of coming back to the routine, slowly, mainly the guys in the East. So give us some tips how to flatten the curve, okay? So we will all be behind this long pandemic and terrible pandemic as soon as possible. So since most of us are this day working at home, so BERMA decided to conduct a series of webinars, 8 webinars for the segment of the waterworks and 8 webinars for the segment of the irrigation, 1 at each week. So right in the end of this webinar, we will get announcement for the next one. So I'm sure it will be interesting. The next one will be 1 week after Easter. So before we start, I will first introduce myself. So my name is Tal Levy. I'm certified as a Bachelor of Water Technology, Bachelor of Science in Water Technology. I'm working for BERMA for more than 6 years now as a waterworks application engineer, supporting our distributors and daughter companies in the area of Europe, Middle East, and Africa. And I have a special expertise in performing surge analysis and sizing and positioning of air valves. I'm pleased to make the first webinar in the subject of optimal selection of air valves. I will try to interest you in this subject for the next 45 minutes. In order to manage this large event of more than 300 right now participants, I have here the help of my 2 colleagues, Mr. Eyal Geller, which is the air valve product manager, and Mr. Roger Mulist, which is the application engineer of the waterworks in BERMA, Europe. So they will, hello Eyal. Hi there.
Good afternoon, everybody. I will try to watch your questions and we'll make a short stop for that. And of course, we will be able to answer some of the questions at the end of the webinar.
So thank you, Eyal. Hi, Roger.
Hi, good afternoon from Spain. Hope you enjoy this webinar.
So Roger and Eyal, both of them will track the chat and the questions during the seminar. I will give some time in the middle of the presentation to answer 1 or 2 questions, and also some time in the end of the presentation. I'm sure it will be interesting. So let's start. Okay, so first of all, let's look together on the agenda. So basically, the main subject will be the following. First of all, we will look together what are the parameters which affect the performance of an air valve. Okay? Then we will look together at a relatively interesting research done by University of Valencia here in Berma Airflow Test Bench, which will test the performance of air valves from global manufacturers. So we look together at the results and the insights. Then we'll say a few words about the uniqueness of Berma Airflow Test Bench. We'll give the attention and discuss about the unique phenomena of premature kinetic closure and the effects and the risk on water pipelines. And in the end, we will give 3 vital guidelines for designers which make selection and sizing of air valves. So first, I would like to, together with you, to count the 4 main needs and requirements why air valves are essential in water pipelines. So first of all, and the most common and popular one that most of the engineers are familiar with is prevention of air pockets accumulation on high points. On the high points, the air tend to accumulate, and some air which is dissolved in the water is being released on those high points which have relatively low pressure, or due to air loss along the line, they are start to be released from the water. And we get air accumulation on those peaks. Of course, that those air pockets create local head loss, and as we have more and more peaks along the line, we get higher head loss, which means that now the pump for the same design flow rate needs to create and to provide higher pressure, okay? That's, in the end of the day, is converted to a higher energy consumption of the pump and for higher cost for delivering the same flow rates. So the first objective of an air valve is to release these air pockets and to maintain on a full cross-section flow. That's the objective of, that's the responsibility of the automatic orifice, a relatively tiny orifice at the size of between 1 to 4 millimeter. By the way, most of the presentation will be in metric units. So sorry for the guys in the States, but I'm sure you will be able to do the conversion quite easily. So the tiny orifice of the automatic feature is relatively small due to the fact that it releases air while the system is pressurized, and opening very small nozzle is enough to release those tiny volumes of air. So that's the first objective, and that's actually the only requirement and mission of the automatic orifice. During this presentation, we won't focus and we won't talk about the automatic orifice. We will focus on the kinetic orifice, okay? The kinetic orifice is responsible for 3 main objectives. The first one is to prevent any vacuum formation during drainage or burst, okay? Whether you are doing a maintenance or cleaning the pipeline and you drain the pipeline from a low point. So at this event, the air valve, in order to prevent vacuum on high points, needs to draw into the line high flow rates fast in order to prevent this vacuum. So that's why we are using a large orifice, the kinetic orifice. So that's the main, the first requirement. The second requirement for the kinetic orifice is to allow safe and controlled pipeline filling within a reasonable time, especially in the irrigation sector, where the pipelines are being filled and drained on a daily basis. So during a startup, the pipeline is full of air. We need to relieve this air in a controlled manner in order not to create pressure surge. And it's also being done through a relatively high a large kinetic orifice, which allow high flow rates. So that's the second objective of the kinetic orifice. The third, and from my point of view, the most important one, is to protect against any transient scenarios, which will lead to pressure surge, water hammer, and in severe conditions to water column separation, okay? For instance, we have a pumping station, and during pump shut-off, the water continues with the momentum to flow forward, while there is stoppage of water flowing from the pumps, and then it means that in between the check valve to the rest of the pipeline, there might develop water column separation and severe vacuum conditions. In order to prevent this water column separation, we need to allow and to draw into the line high flow rates of air, high volume of air, and fast. So that's also being done through the kinetic orifice. So basically, these three objectives are being achieved by the kinetic orifice. And in case where the performance of the kinetic orifice is not good enough, or it's not sized correctly, so it will have a direct impact on the achievement of one of those goals, okay? So if the kinetic orifice is too small, there is a chance that the pipeline will be collapsing due to vacuum conditions, or will be a rupture due to pressure surge. So let's watch some three nice photos showing what can happen in cases where the pipeline suffer of severe vacuum. So that's a stainless steel pipe, completely smashed. Another photo showing relatively large diameter pipe, also completely collapsed due to vacuum. Most of these photos are referring to, are taking from relatively large pipelines, large diameter, which are more sensitive for vacuum. And this picture I like it the most, it's showing us what happened if the pipeline is buried underground, okay? So again, it's totally smashed and implode into itself, and you can see what happened to the land above it. So the following slide shows us how to read and how to understand what is the performance and the capacity of an air valve. So what we are looking at right now is the performance, the graph performance of the kinetic orifice, whether it's part of a kinetic air valve or whether this kinetic orifice is part of a combination air valve, okay? Just reminding you, combination air valve, it has the two functions in one product, both the kinetic and the automatic feature. So this vertical axis is showing us the air pressure in the pipeline, not the water pressure. Remember, the kinetic orifice, due to the fact that it's getting into action only in transition scenarios, whether it's pipeline filling, drainage, burst, water hammer, but not while the system is pressurized. So that means that the pipeline is not in a full cross-section flow, and we are talking about much lower pressures compared to what we are used to work with water. So in case that during pipeline filling, the pressure increases to positive values of 0.1 bar, or let's say 0.3 bar, which is plus 3 meters, we can see that the kinetic orifice will allow outflow of 3,000 cubic meters per hour, okay, for a 4-inch, which this graph refers to C70, which is a combination air valve, PN40, one of Bermat products. On the other end, if you look at the negative value in case of vacuum conditions, okay, the same, but now in minus 0.3 bar. the same product 4-inch will allow only 2,500, okay? So as you can see that those graphs are not symmetric. And the reason for that, that's actually the physics. We learned by making measurement of which reflecting what happened in pipelines in the field. So we learned from those experiments that for the outflow, for the outflow through an air valve, the flow is getting choked at pressure of plus 0.9 bar. Okay, so means that if we increase the pressure above 0.9 bar, still we won't get higher flow rates. On the other hand, during vacuum conditions, below 0.5 bar, not 0.9, 0.5 bar, we already get this phenomenon of choke flow. So that brings us to the fact that those graphs of the real performance are not symmetric. Okay? So, by the way, this type of graphs you can find in any manufacturer that publishing data about its air valve. It will probably share with you also this kind of graphs. Now I would like to show you a similar graph, but this time the same product, but with mushroom cover. Mushroom cover, that's a different cover, which has holes all the 300 degrees all around. And those holes has equivalent area, which is larger compared to the same product, but with down cover. So we can see that at plus 0.3 bar, the same 4-inch, but with mushroom cover, bring us more than 4,000 cubic meters per hour. And the reason that I'm showing you that is the following, that you can see the first factor which affect directly and quite dramatically on the performance, which is the type of the cover. We can see that with the mushroom cover, the flow capacity is almost 30% higher compared to down cover. So that's the first factor which affect the performance. The second factor, which is not less important, is actually the size of the kinetic orifice. Friends, what we are looking at right now, these two air valves, if we will consider them in a tender specification, both of them are defined as 6-inch, okay? Because we define the size of an air valve based on its connection size. So both of them has a flange of 6-inch. However, and this is the kicker, you can see that the red one is dramatically reduced bore. The real passage of flow through the device is only 80 millimeter, while this one is a pure full bore orifice of 150 millimeter. Okay? So the second very important factor is what is the size or the actual passage of the kinetic orifice inside the product itself, and not only the connection. So at this slide, I would like to summarize and to come together with you the three main factors which affect the performance of an air valve. The first of all, that's the size of the kinetic orifice. What we are looking at right now, it's the cutway of the C70, okay? So the size of the C70, it's defined by the inlet size, which is this diameter over here. However, the kinetic orifice is the top plate, the stainless steel top plate located at this point where the float is sealing against. So the size of the kinetic orifice in some products can be much smaller compared to the size of the inlet. In the C70, it's a full bore air valve, so both the inlet and the kinetic orifice are at the same size. So first factor to look at is the size of the kinetic orifice. The second factor, as we saw, the big difference in performance is the type of the cover. So obviously that mushroom cover will bring higher performance compared to the down or the side. And the last factor which is not less important, is actually the efficiency of the flow curve through the device, through the air valve. You can see here in this demonstration that as those curves are more straight with less angles, means that the product will allow higher flow rates and will create lower head loss. Same like what we are doing with the 700 series valve or the 100 series valves. The only reason why they are Y pattern oblique is in order to create minor head loss to allow as much as possible flow capacity and to create the flow through the control valve semi-straight. And that's what allows us to create and to generate such high flow rates. Another important point while we are looking at the cutway of this product, as you can see, all bare mud air valves are in the shape of an egg. The reason for that, in order to create the flow to be as much aerodynamic as possible, okay? And in addition, there is an area, if we look on the area between the float, okay, to the body itself. It's some kind of a ring, okay, between the float to the valve body. And it's very important during the design to make sure that this ring doesn't create any bottleneck for the flow. And the total area of this ring is at least larger than the size of the inlet and the kinetic orifice. So those are the three main factors which will affect the performance of the kinetic orifice. And before moving forward for the research, I will give some time, couple of minutes for questions. So please.
Yeah. There are two questions here which I would like you to refer. First of all, you didn't mention till this point the pressure rating or the operational pressure of the air valve. So please refer to that. And the second question is there any single coefficient that reflects the airflow capacity of an air valve, like a KV or CV value for hydraulic control valve, for example?
Okay, so regarding to the pressure rating, basically, same like hydraulic control valves, we are talking about products which are rated as a PN16 or PN25, PN40, and that refer to the inland pressure while the system is in normal operation, pressurized with water. So it means that the body itself, the bolts, the entire structure will be able to stand 16 bar or 25 bar. But that's has nothing to do for the performance of the air valve during operation of air intake and air exhaust for the different scenarios that I just explained. So that's about the pressure rating, and I hope it
okay.
the answer.
The second question was regarding the KV or CV value, which is very common when we are referring to hydraulic control valves. So is there any equivalent coefficient for air valves?
Okay, so basically, this is true. You know, I mentioned the fact that one of the factors, okay, that's the internal design of the control valve or of an air valve, but in hydraulic control valve, it's a well-established market. So the manufacturers have this factor which allows them to compare the efficiency or the flow capacity of one product compared to another by only one factor, which is the KV value. However, apparently in the air valve market, the manufacturers doesn't have this information. Okay, there is in the technical literature, they mentioned something which is called the CD. Okay, the CD is taking into account all those factors together, and considering only the size of the nozzle, you can say whether this nozzle will allow for the same diameter higher flow rates compared to a different nozzle, okay, in the same size, but in a different shape maybe. This CD value, it runs between 0.45 to 0.57 or 0.6, but honestly, none of the manufacturers, or at least majority of them, doesn't really know what is the CD value for each one of their product, and this value changes between size and between models, and it's very difficult to measure. So that's why in the field of air valves, we don't have any single value which we can compare the capacity of different products. Okay. So I will move forward in order to meet the schedule of 45 minutes. I'm preparing you. It might take a little bit longer, but I promise not to create too much delays. So we will start now and moving forward for the research. So basically, this interesting research, it's being done by University of Valencia. They contacted 2014 to BERMAD, asking permission to use our one-of-a-kind airflow test bench, okay? In the next slide, I will explain exactly why this airflow test bench it's so unique. And they conduct a relatively wide and interesting research of collecting air valves from global manufacturers worldwide, make measurements of the performance, and to give answers for several questions, which one of them was, is it correct to choose an air valve based on its inlet size, okay? We will give an answer for these questions in the end of presentation, which I'm sure most of you already can think about the answer. So basically, the complete version of this study you can find in the internet. Look for comparative study of intake and exhaust airflows of different commercial air valves. In this case, I found it in the website of Science Direct, and you will be able to read the entire process, all the insights, and that's quite fascinating and interesting. So, BERMAD airflow test bench. We got it into the market of air valves about 10 years ago, and we decided that we want to have a facility which will create and make hydraulic conditions or aerodynamic conditions which are the most similar of what happened in real pipelines in the field. And that's why we came out with this unique concept of airflow test bench with a very large blower, which allows us to do two things. The first of all is to make a continual measurement. That means that we can now keep both the air pressure and the flow rates constant for several minutes, and to make several measurements to make sure that the measurement and the result is really consistent, okay? Some of the manufacturers does have also airflow test bench, but those test facilities have a different design and different concept. They rely on the concept of having a pressurized vessel. Let's say in the size of 5 or 10 cubic meter, discharge charged with a pressure of, let's say, 1 or 2 bar, and then they open a valve fast and allow the pressure and the air from the tank to flow to the pipeline through the air valve, and by that to measure the outflow through the device. First of all, the pressure vessel is being drained very fast, and that doesn't allow to make any continual measurement. But the second factor, which is even more important, is that in order to measuring the inflow, okay, from the environment into the pipeline, they connect the pressure vessel on the cover of the air valve, and that means that outside of the air valve there is positive pressure, while in the pipeline there is still zero, but not a real vacuum condition, not a real negative pressure like we have during scenarios of drainage or burst in the field. So, and we will see in a bit that brings a pretty dramatic deviation in result. While the concept that we have here in the airflow test bench allows us to create real vacuum conditions in the pipeline, while the surrounding, of course, it's still zero, and by that to measuring the inflow through the air valve. Of course, that the airflow test bench is certified and approved by both the European and the Australian standards. And I would like to share with you some nice video showing measurement experiment of C70 3-inch with down cover. And during this video, you will hear the very loud noise, okay? And we are talking only of pressures of 0.3 or 0.4 bar, which is considered in water relatively low pressure. However, in air, this is brings very high flow rates, which are very noisy. So along this video, I will stop every now and then for give some explanations. Okay, so now the operator is increasing the pressure. You can see in this gauge the pressure. So this is 0.1 bar. It will reach up to 0.45 bar. And you can see the outflow through the device. So at pressure of plus 0.45 bar, this product will lift about 2,500 cubic meter per hour. Okay. I will move it forward, showing you the vacuum conditions. So you can see here that it says air forward. It means outflow from the pipeline to the environment. So we have this nice toy here, the smoke machine, in order to get a visual demonstration of the inflow. So increasing and creating vacuum conditions, you can see here in the gauge the negative values, okay, minus 0.1 bar, minus 0.2 bar. And air in reverse, it means that now the inflow is 1,500.
Well, we don't hear the videos. Maybe you will open it only for a couple of seconds, so we'll have some real effects of the noise.
Sorry again?
We don't hear the sound of the video.
Okay.
So, consider to open it maybe only for 3 or 5 seconds, so we'll get an impression of the sound.
Okay. I would like to press. Tell me if now you can hear it, please.
Yes.
Good. Okay, so as you can see, it's quite noisy. Okay. So, and also, as you saw, that the outflow and the inflow are not the same values for the same pressure of plus 0.4 bar or minus 0.4 bar. So that's a really nice and one-of-a-kind facility, and that's the reason why University of Valencia decided to come here and make 2 full weeks of measurements without the intervention of BERMAD. So now let's move for the result. So they decide to focus on a medium size of fringe collected from a different 13 different manufacturers, and in the end they reached to almost 1,800 measurements. Okay, you can see here a picture of some of the ovals, and that is the result. Quite interesting, different colors. Okay, in order to make apple-to-apple comparison, all of them are fringe. And what we can see here is the following. Again, we have the pressure, we have the flow rate, positive values for outflow and negative values for inflow. And if we will take, of course, that each curve, each color represent a different model, okay? While all of them, in the tender specifications, they are considered as equivalent product, okay? Because all of them defined as a 3-inch air valve. But look, for example, on this red curve here, that for the inflow of minus 0.4 bar allows about 400 cubic meter per hour, while there is another product which allows, or some other products allow more than 1,500, or some of them even reaches to 2,000, okay? You can see also the big difference for the outflow, which is quite obviously. And I must say that the first time I look on those graphs, I was quite in shock, okay? Because if you are taking the field of, let's say, hydraulic control valve, so sometimes you can expect that there will be a difference in the KV value from one product to another at ratio of 50% higher or 70% higher or even 100% higher. But here it's higher in 500%, okay? We have ratio of 1 to 5 in performance between some of the products to other products. So that was just unbelievable. And considering this quite astonishing result, it's obviously that each one of us as designers must to pay attention and to choose air valve not based on its inlet connection, okay? But based on its real flow performance, okay? Flow, its real capacity. So that was certainly an interesting graph. The green one over here refers to C70 down cover, while the orange is the C70 with mushroom cover. The next graph is also quite interesting. It's focusing on 3 different manufacturers. Each one of them is represented by a different color. The solid line is showing what the manufacturer published in the product catalog page, okay, in the data sheet, while the hash line showing the measurements in the experiment itself. So you can see that for the outflow, all the 3 products, most of them are quite match between the publications to the measurements. However, for the inflow, there was a big difference. For instance, you can look at the blue model, which is publishing in the catalog page that it be able to allow at minus 0.4 bar, almost 3,000 cubic meter, while in reality, this product introduced into the line only minus 1,000, okay? So there is a big gap. And actually, I want to believe, and I'm quite sure that most of the manufacturers doesn't do it in purpose, but since that most of them doesn't have any airflow testbed to make the measurements, so they rely on the concept of making, on publishing those curves based on physical formulas, which are not always matching to what the real capacity of the product. While some of the few manufacturers which do have airflow test bench, they have the concept of a pressurized vessel, which as I explained before, mainly for the vacuum conditions, bring quite significant deviation or inaccurate result. So that's another suggestion for you as designers. While you are getting and starting to think about and considering using one of the products of some of the manufacturers, so contact to the manufacturer and ask them to give you a declaration from where they took this data from, whether it's based on a formula, and if it's based on a real measurement from an airflow test bench, so that they will give you the values of the actual measurement and the formal statement from the airflow test bench. Okay. So just before we finish, I would like to share with you the interesting phenomena of premature kinetic closure. Okay, the premature kinetic closure, it's something which happens in any air valve due to the basic fact that the float itself doesn't made of wood or metal. It's made of a lightweight material which must to float on the water while it reaches to the air valve in order that the air valve will seal and won't leak. So in any air valve, there is a point where the outflow, the flow rates are very, very high during pipeline filling or during a pressure surge. And the velocities are high, and that's create a situation where the float is being lifted up, dragged upwards, and the air valve closes prior to the arrival of the water to the air valve. So that means that now the air valve is completely closed, while there is still volume of air trapped in the line. And that can lead to two things. First of all, that can lead to pressure transients due to the fact that air it can compress and expand very fast. And the second factor, which is not less important, that it will stop completely or will slow down dramatically the filling of the pipeline, okay, the filling process. And if we are talking about national pipelines, large diameter pipelines, so that means that now the downtime of the pipeline is much longer, and of course that there will be some it will increase the cost of making this maintenance, okay, and the impact on the citizens and the consumers. So the premature closing is something which happens in any air valve. The question is whether it happens in pressure of plus 0.4 bar or 0.5 bar, or it happens in pressure much lower, which is let's say +1 or plus 0.5 meter, okay, +1 meter or 0.5 meter, which is somewhere around here. So that's also something that University of Valencia made the test, and you can see here models with titles from A to N. So you can see that some of the products closed at pressure of 2.25 bar, which makes sense because during pipeline filling, designers consider that the pressure of 0.2 bar, which is plus 2 meters, is relatively high pressure during pipeline filling. So if an air valve is closes, the kinetic premature closure, it happens above plus 2 meters, so that means that very likely that the air valve will do its job and you won't expect any issues. However, in cases where the premature closure happens in lower values, below 2 meters, then you might have issues, and you can see that some of the products here, like for instance, the model E or G, closed already at pressure of 0.3 meter. Okay, those values are here in bars, so this one and this one is only 30 or 70 centimeters of pressure. So very likely, so those will close before relieving all the volume of air. In this case, model D, it's the C70 with down cover. And now let's move for the last part, friends. The summary. So back to the research questions, which is quite obviously, is it correct to choose an air valve based on its inlet size? Then of course the answer is big no. Okay. And I would like to share with you 3 guidelines, which I see them as the most vital recommendations for designers who make sizing and positioning of air valves. So first of all, pay attention for the size of the kinetic orifice, okay? I get during a week's few or several project specs that in most of them, it's well clear to see that the specifications are referring only to the size of the connection. So please, as designers, put also in the specification the size of the kinetic orifice. The kinetic orifice is the bottleneck of the flow through the device, and it must be defined clearly in the specification. So the first point is the size of the kinetic orifice. The second one is to choose an air valve based on its real airflow curve, okay? And make sure that it's based on a certified airflow test bench, okay? So that's something that any designer that you want to, you consider to use its air valve, ask them to share with you where they get the data from. And the third rule is to make sure that the air valve doesn't close below 2 meters. Okay, that the premature kinetic closure is not happening below 2 meters. I can tell you one thing, that all the manufacturers doesn't publish the premature closure. In all their publications, you will see that the curves continues to plus 0.4 or even 0.5 bar. Even in this particular product, the air valve closes much earlier. Perhaps they don't know this value, or perhaps due to the fact that all the other manufacturers doesn't publish this value, so they don't publish that either. But ask for the manufacturers to get this value for the air valves that you plan to specify. So these are the 3 fundamental guidelines that, from my point of view, it's very important to consider. So guys, We made it in about 50 minutes. First, I would like to thank you for your time and listening to my voice. We will have time now for allowing a few questions, and just would like to share with you the fact that BERMAD, for many years, we are making and performing surge analysis and make sizing and positioning of air valves. So feel free to contact us and we will give you this service. So you are welcome to contact us, whether it's through the website or through the distributors. And we are here, and thank you very much.
Tal, we have some questions since we are already almost towards the end of this webinar. I will just pick up one question, and that we will review all other questions as well as the remarks from the chat, and we will answer them and refer to them later on. The question which I select, there is, can you please refer, how do I choose an air valve size? So please refer in short to some of the principles for sizing, and also is there a rule of thumb, for example, in proportion to the main pipeline diameter?
Okay, so that's quite an interesting and popular question. So I know that many of the designers are used to make the selection of an air valve in proportion to the main pipe diameter, let's say in the ratio of 1:5. So if the pipeline is 20 inch, so I will select 4-inch air valve. However, I don't like this approach, okay? We need the best method is to run an analysis based on one of the software, like BERMAD offers the BERMAD Air, which illustrate scenarios of pipeline drainage, burst, pipeline filling, etc., and then to perform surge analysis. But if you don't have this luxury and the time of performing a complete analysis, you can use the following rule, okay? The rule, which is taking into account not the pipe diameter, but the flow rate, okay? Because in the same diameter, we can have quite a wide range of flow rates. You know, most of the designers are used to design at the flow rates of between 0.5 to 2.5 meters per second. So for this reason, since during water column separation, the intensity of the water column separation occurs in direct proportion to the velocity in the main pipeline, I will choose the air valves, the size of the air valve in proportion to this velocity, means in proportion to the design flow rate. So let's take this example, okay? So let's take, for instance, that in the system, I have a flow rate of 1,500 cubic meters per hour, okay? So I will draw, let me just use this nice feature here. So let's draw a vertical line at minus 1,500, okay? And in parallel, you remember all those nice photos of showing pipelines collapsing. So this is something that happens in different values, depends on the pipe material, diameter, and wall thickness. But generally speaking, of course, it's stiff and rigged pipes like made of metal are less sensitive compared to PVC or HDPE. But let's take some safety margin and design that we don't want to allow negative pressure, which is lower than minus 0.15 bar, which is 1.5 meter, okay? That's considered as already quite severe negative pressure, and I don't want to cross this value. So let's draw an horizontal line at minus 0.15 bar, and we get this point here, okay? So that's the system requirement for the given pipeline, for the given system. And now let's see what a 3-inch air valve can allow at minus 0.15 bar. At minus 0.15 bar, 3-inch can allow only 1200. Okay, so means it's not enough. So I need to go to one size larger, and we can see that the 4-inch at this pressure can allow 1800. So for this particular case, I will choose a 4-inch air valve. So that's my the rule of thumb that I'm using, and I think it's much more precise and accurate method compared to taking account only the diameter, the pipe diameter.
Okay, Tal, thank you. I think that we have to say again a big thank you to all the participants. We're wishing you, first of all, to be healthy, to you and to your family, and hoping for healthier times in our world, and happy Passover. So
thank you, Eyal. And again, I would like to thank you as well. Really appreciate your efforts in joining to this webinar. We have 300 attendees, and that's quite impressive. So, and then I hope to hear from you very soon, and stay safe. Thank you very much. So at this stage, if you have any other questions, feel free also to send us through the subsidiaries or through the website, and we will be more than happy to answer. And at this stage, we will finish the webinar. So thank you very much, everyone. Bye-bye. Be safe.